Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we will begin our discussion of functional groups that's commonly observed in organic compounds. Before we discuss very specific functional groups, I want to draw your attention to these three hydrocarbons that we discussed in the previous chapter: alkenes, alkenes, and alkynes. And so if you guys were to look at the elements that make up these hydrocarbons, you'll see that alkenes, alkenes, and alkynes are primarily composed of carbons and hydrogens. Imagine that you guys were organic chemists and you're tasked to build molecules exclusively using carbons and hydrogens. Even though there's like an infinite number of ways for you guys to create these molecules, primarily from carbons and hydrogens, at some point in time, the work can get kind of dry because you're only working with like two elements. And so what makes organic chemistry really, really fun and exciting is this idea of functional groups. The idea of having or working with heteroatoms, elements that are not carbons and hydrogens, and seeing what type of chemical reactions or what type of physical properties these new substances will have. And so overall, the main purpose of a functional group is to provide or give new physical and chemical properties for these organic compounds that's primarily composed of carbons and hydrogens. And so one way for you guys to think about functional groups is icing on a cupcake. And so the cake itself is good on its own, right? It's just okay. But the moment you add like a proportional layer of some type of flavored icing, whether it be like chocolate, lemon, or vanilla, overall it kind of uplifts that dessert, right? It creates a different texture for that dessert, if you will. And so, very similar to this idea of icing on a cake, that's what functional groups are to organic compounds. So functional groups are these heteroatoms that gives that specific organic compound different physical and chemical properties so that it can undergo different types of chemical reactions, producing different compounds that can be used in industry, for example, creation of plastics or a specific fabric that can be used to make a new different type of clothing. It can also be used to synthesize new drugs and medicine. And so I'm going to go ahead and scroll through this list of functional groups that you guys see on this slide. And as I'm scrolling through this list, I want you guys to observe, the different types of elements, the different ways that it's arranged in the in the compound. And so even though these heteroatoms are primarily like oxygens and nitrogens, and here we have sulfur, just even the way that they're arranged, whether or not they have a single bond or a double bond, and if it's in the middle of a compound or if it's at the very end of a compound, these functional groups, they give new physical and chemical properties to that organic compound. Now, the five functional groups that we're going to be discussing in this chapter are alcohols, ethers, aldehydes, ketones, as well as thiols. Not specifically in that order, but those will be the five functional groups that we're going to be focusing on specifically in this chapter. Other functional groups such as amides, esters, carboxylic acids, amines, it'll be seen in a different chapter. So let's go ahead and get started. The first functional group that we're going to discuss are alcohols. And so you guys have crossed paths with the word alcohol once before. Maybe the word alcohol has been, dropped in a conversation that involved, liquor, or having a good, fun night. The word alcohol can also be used in a sentence that involves like hand sanitizers, and the list continues. And so all of these products, these consumer products, such as like beer and hand sanitizers, disinfectants, the list kind of goes on. They all have a functional group that's in common, which is an OH. And so alcohols are a class of organic compounds that contain a hydroxyl group. And a hydroxyl group is simply this oxygen that's covalently bonded with this hydrogen. And so we have seen this combination of OH before when we were talking about, when we were discussing concepts in inorganic chemistry. And so that combination, that OH group, another way that you guys have seen this before is hydroxide, right? And so hydroxide is a polyatomic ion in which the OH has a negative charge. And so this negative charge is indicative of an anion in inorganic chemistry. And so typically these anions are going to ionically bind to a cation. And so all of these vertical lines that I'm drawing, it's going to represent an ionic interaction or an ionic bond, which is simply like this attraction between positive and negative charges, if you will. And so this sodium is our metal, and it's going to serve as our cation. And so if you have this OH that's ionically bonded to a metal, then that OH is going to be considered a hydroxide. However, if you have an OH that's covalently bonded to an organic compound, then that OH is going to be referred to as a hydroxyl group. And so we can go ahead and generalize the attachment of this functional group, this hydroxyl group, onto an organic compound by drawing a squiggly line. And so what this squiggly line represents is, any organic compound or any hydrocarbon. Let's specify it that way. So any hydrocarbon. So this OH can be on a methyl, an ethyl, it can be on a pentane, a nonane, the list just kind of goes on. And so these hydroxyl groups, they can be represented in a skeletal structure by simply writing OH and then that covalent bond, much like you guys see here in this image. And so let's just say that we have pentane. Pentane, there's 5 carbons. And so if you guys wanted to depict a hydroxyl group in skeletal structure, what we're going to do is we're going to create a covalent bond between this carbon and the oxygen and the hydrogen. So it's not really necessary for you guys to draw a covalent bond between oxygen and hydrogen. You guys can, but we're going to go ahead and just expedite our structure by writing oxygen right next to a hydrogen. And it's already implied that there's a covalent bond between them. And so basically these alcohols, these hydroxyl groups, can be found within the structure of an organic compound. That's why I put the parentheses. Or it can be found in the terminal ends of an organic compound. So this area, I'm going to go ahead and call that, within. And I'll go ahead and do this in another color. So these ends are terminal carbons. And so you guys can go ahead and basically place an alcohol within an organic compound, or you guys can place them terminally. And so one of the things that we can do with alcohols is classify them based on what carbon they're attached to. And so alcohols can be classified by the number of carbons bonded to the carbon that it is attached to. And so what do I mean by that? So let's just go ahead and look at this image right here. So notice that this alcohol, this hydroxyl group, is covalently bonded or attached to this carbon. And so this carbon is going to be covalently bonded to this carbon. So because this carbon in pink, this central carbon in pink, is attached to only one, or covalently bonded to one carbon, then it makes this alcohol a primary alcohol. So primary means one, meaning that the carbon that the OH is attached to is covalently bonded to one carbon. Okay. And so here I just wrote it down. A primary alcohol has an OH group on a carbon that's covalently bonded only to one carbon atom. And so we're talking about the central atom being covalently bonded to another carbon. And so typically primary alcohols are found on the terminal ends of an organic compound. And we'll see that as we go through different examples in just a second. And so we can also classify alcohols further by using this word secondary alcohol. So a secondary alcohol has a hydroxyl group that's on a central carbon, in which that central carbon is bonded only to two other carbon atoms. And so looking at what this means in terms of a visual basis, so this is our central atom, and this central atom is covalently bonded to this hydroxyl group, but it is also covalently bonded to two carbons. And so therefore it would make this alcohol a secondary alcohol. And so if you guys look at this image, we can classify this alcohol as a tertiary alcohol because the carbon that this OH is covalently bonded to is bonded to 1, 2, 3 other carbons. And so it would make this alcohol tertiary because this carbon is covalently bonded to 3 other carbons. And so quaternary alcohols do not exist. And the reason why that is because remember, carbons can only bond 4 times. And so if, for example, you were to have another carbon over here, another CH3, this would be an example of a quaternary alcohol. But if you look at the number of bonds, this would be 1, 2, 3, 4, 5, which breaks the octet rule that carbon wants to abide by. And because adding another bond would break the octet rule, quaternary alcohols do not exist. So tertiary is the highest that it can go. Okay. And so tertiary and secondary alcohols are typically found, embedded within the compound. And so if you guys are looking at the example that we drew earlier, here we have pentane. If we have an alcohol here, or a hydroxyl group here, let me zoom in real quick. Then this carbon, the central carbon that this alcohol is covalently bonded to, is covalently bonded to 2 other carbons. And so this carbon would be considered secondary, making this alcohol also secondary. And notice that it's embedded more or less within the structure. It's not found on the terminal ends. So the same holds true for tertiary alcohols. So for example, we can have, let me just draw this in blue. We can go ahead and have a molecule that looks like this. So this carbon is covalently bonded to 1, 2, and 3 other carbons. And so this carbon would be considered a tertiary carbon. And if there was an alcohol attached to this, it would make this alcohol a tertiary alcohol. But once again, notice that it's typically embedded within the molecule and it's not found on the terminal ends of an organic compound. Okay, so this labeling, this classification of alcohols is going to be revisited when we're talking about chemical reactions that involves alcohols. So for now, we're going to go ahead and do a quick learning check. We're going to classify the following alcohols. So here I've depicted the condensed structure of what an alcohol might look like. And so if we're looking at this example, here we have the alcohol that's covalently bonded to this carbon. So this carbon is going to be our point of reference. And so this carbon, this central carbon, is covalently bonded to 1, 2, 3 other carbons. And so it would make this carbon tertiary, making this alcohol tertiary as well. And so overall, we would classify this molecule as a tertiary alcohol. So in this second example, our hydroxyl group, or our alcohol, is found pretty much in the end of this organic compound. And so if you recall the idea behind condensed structures, basically this heteroatom is going to be covalently bonded to this carbon, making this carbon the central carbon with respect to the alcohol. And so since this carbon is only covalently bonded directly to one other carbon, this carbon is going to be considered primary, making this alcohol primary as well. And so if we're looking at this example, notice that our alcohol is right here, and there is a covalent bond to this carbon. And so this carbon is going to act as our reference point with respect to the alcohol. And so if I treat this carbon as my central carbon with respect to the hydroxyl group or the alcohol, and if I look at the bonding of that central carbon, it's going to be covalently bonded to two other carbons. And so since it's covalently bonded to two other carbons, it would make this carbon secondary, and therefore it would also make this alcohol secondary. So we can go ahead and classify that last example as a secondary alcohol. Okay. And so hopefully you guys were able to follow my train of thought in terms of classifying alcohols based on looking at the condensed structure. So sometimes looking at the condensed structure and classifying the alcohol is a bit tough because you have to kind of skip the hydrogens, right? So just imagine that these hydrogens are surrounding the carbon, and it's not so much that this carbon is bonded to this hydrogen and this hydrogen is bonded to this carbon. It doesn't work that way. These three hydrogens are surrounding this carbon. All right, so let's go ahead and look at classifying the following alcohols through the skeletal structure. So this one is probably a little bit more straightforward, just because you guys can see the direct connection between the alcohol and the carbon. And so looking at the first example, notice that my alcohol is covalently bonded to this carbon. So I'm going to use this carbon as my focal point to classify my alcohol. And so if I switch this to green, the carbon that I've marked in pink is covalently bonded to one and two other carbons. And so it would make this carbon a secondary carbon, thus making this alcohol a secondary alcohol. And so if you were to follow that same logic for the rest of these examples, here's our alcohol. It's covalently bonded to this carbon. And this is going to be the carbon that we're going to look at as our reference point. It's going to serve as our central atom. And you'll notice that this carbon that's in pink is going to be covalently bonded to, let me just change the screen. It's going to be covalently bonded to one other carbon, making this carbon a primary carbon. Thus, the alcohol is classified as a primary alcohol. And so if you guys look at this example, once again, this primary alcohol is found on the terminal end of the carbon, whereas this secondary alcohol is found right in the middle. It's kind of embedded inside the organic structure. So looking at these two other examples, we're going to find where the alcohol is located, trace back the covalent bond to its central carbon, and then we're going to kind of branch out just by one carbon. We're going to so here this carbon in pink is covalently bonded directly to one other carbon. And so therefore, it'll make the carbon in pink a primary carbon, thus making this alcohol primary as well. Last but not least, here I have a different depiction of this organic compound. Here we have the alcohol. It's covalently bonded to this central carbon. And this carbon that's marked in pink is covalently bonded to 1, 2, 3 carbons, making this carbon in pink a tertiary carbon, making the alcohol that it's attached to also tertiary. Okay. All right, and so hopefully you guys get the trend on how to classify these alcohols. So go ahead and take a moment to classify the alcohols for both of these carbons. And so if you guys said primary, then you're correct. So once again, we have this alcohol that's covalently bonded to this carbon. And this carbon in pink is covalently bonded to one other carbon, making it primary. Okay. And the same can be said for this alcohol too. It's going to be a primary alcohol. All right, so let's go ahead and talk about the polarity and physical properties of alcohols. And so if you guys are looking at the structure of the alcohols, and if you take in consideration the lone pair that's on the oxygen atom, and so I'm going to go ahead and focus on methanol over here. And so I haven't drawn it in the previous representations of alcohols, so you guys don't have to draw in your lone pairs. But technically speaking, remember that oxygens, they need to follow their octet rule. They need to follow the octet rule. And so we need to make sure that all of the oxygens contain or have 8 electrons, whether it's shared or owned. And so if you guys are looking at this oxygen in methanol, notice that we have 1, 2. So 1, 2 electrons, 3, 4 electrons. And the other 4 electrons to make our octet is going to be found as 2 lone pairs. So here's one lone pair, here's a second lone pair. And so if you guys are talking about electron geometry, we have 1, 2, 3, 4 groups of electrons. And so if we have 4 groups of electrons, the electron geometry is tetrahedral. And the molecular geometry is going to be bent. So remember, molecular geometry does not take into consideration the lone pairs. Only the covalent bonds, or the bonds, the electrons that form the bonds. All right, and so if you guys are looking at this ball and stick model of methanol, notice that overall it has this bent shape to it. And the angle of that bent shape is going to be less than 109.5. And so the main reason why I'm discussing this is the way that we're supposed to depict our alcohols in the skeletal structure, which you guys have seen in prior examples. Notice that here we have like this bent type of configuration for the alcohols. And so we're trying to capture its molecular or electron geometry in some form when we're writing these skeletal structures. And so if you guys are looking at the structure of alcohols once again, and you guys are specifically focused on the covalent bonds or the classification of the covalent bonds, remember that oxygen is a very highly electronegative atom, second to fluorine. And so if you have oxygen that's covalently bonded to hydrogen, the electron of hydrogen is mostly going to be found on oxygen, right? There's an unequal sharing of these two electrons that creates that covalent bond, such that hydrogen's electrons is more attracted towards oxygen. And so what that does is that it creates polarity in the bond, creating a polar covalent bond. So this is going to be a polar covalent bond. And since the dipoles of these polar covalent bonds points in the same direction, also because these also because of the presence of the lone pair on oxygens, there's going to be a net dipole that's pointing in one direction. And so the main concept or the main idea that I'm trying to convey is that alcohols are polar functional groups. And so because alcohols are polar functional groups, when it's attached to a hydrocarbon that's mostly nonpolar, it could change the physical properties of that specific compound. And so let's go ahead and talk about the consequences of having a polar functional group on a organic compound. And let's start very small. And so this molecule right here, CH3OH, this is our simplest alcohol, organic compound. That's an alcohol. It's a one carbon organic compound with an OH group attached to it. And so this substance is typically known as methanol. And so if you guys can imagine, let's just say that this OH was not there and we only have CH4. Methane, just this carbon and hydrogen, because it only has carbons and hydrogens, and because their electronegativities are very similar to each other, a CH4 or a methane is mostly non-polar. But when you substitute one of the hydrogens from methane and you add in an OH group, an alcohol, or a hydroxyl group, what that does is that it allows the molecule to hydrogen bond with another polar molecule. And so the addition of a polar functional group allows that whole entire molecule to be able to hydrogen bond with other polar molecules. And so this has some very specific consequences when you guys are talking about physical properties. And so I want you guys to recall that hydrogen bonds are very strong intermolecular forces compared to all of the intermolecular forces we discussed, such as dipole, and London dispersion force. And so since hydrogen bonds it's a stronger attraction between two molecules, that means that it takes more energy to pull them apart. So I'm not too sure if you guys have ever played with like magnets in the store. Some of them, like very weak magnets, you guys can pull apart very easily. So you can kind of attribute that to like London dispersion forces. But when you're talking about stronger magnets, then it would require, more investment in terms of physical energy and physical output to separate those two magnets apart. And so that's what's happening with hydrogen bonds. with respect to dipole-dipole and London dispersion forces. And so having this polar functional group, hydroxyl, on this non-polar substance, which is going to be methane, not only creates a new molecule called methanol, but if you guys have a mole of methanol, then those methanol molecules are all going to interact with each other through hydrogen bonds. So hydrogen bonds are their strongest form of interaction. So they'll also have like London dispersion forces and stuff, but hydrogen bonds is the dominant intermolecular force. And so because hydrogen bonds are the dominant intermolecular forces, in terms of physical properties such as melting point and boiling point, it's expected for these alcohols to have a higher boiling point or melting point compared to its alkane, compared to the alkane version of itself. And so if you guys are looking at this chart, you'll see that methane, so methane, let me highlight this. So meth, eth, prop, bute, pent, hex, they're all describing a specific number of carbons in that organic compound, where meth is 1 carbon, eth is 2 carbons, prop is 3 carbons, bute is 4 carbons, pent is 5 carbons, hex is 6 carbons. And so you'll see that root word, if you will, on alcohols as well. So we have methanol, ethanol, propanol, butanol, pentanol, hexanol. And so when you guys are comparing alkanes and alcohols with the same number of carbons, and if you look at their boiling points, notice that it's tremendously different with respect to each other. Methane, a 1 carbon organic compound, has a boiling point at negative 164 degrees Celsius. So at room temperature, which is 25 degrees Celsius, methane is already in gas form. And so if you wanted, something that's, if we wanted liquid methane, we would really have to lower that temperature below the boiling point. However, the moment you attach an alcohol to methane, the boiling point is going to be 65 degrees Celsius, right? And so this tells us that the addition of simply adding an alcohol, simply the addition of this OH group, allows this typical non-polar hydrocarbon to be able to have a boiling point that's greater than 25 degrees Celsius. Okay, so I'm not too sure if you guys, if I'm conveying that argument correctly, but it's just amazing. Like you just add an OH to a molecule, and then boom, your boiling point is a far, far, far greater than its like original structure, right? And it's this idea of these molecules being able to access different types of intermolecular forces that are much stronger than if you just have CH4 with CH4. And so, by the way, if you have CH4 with CH4, those are London dispersion forces, which are very, very, very weak intermolecular forces. You can pull them apart very easily. Whereas if you guys have hydrogen bonds, these stronger intermolecular forces, you need a lot more energy for them to separate. So with respect to the transition of a molecule going from liquid to gas, you really need to put in a lot of energy to separate out those molecules in liquid form so that it can evaporate and turn into a gas. And so the main conclusion is that if you have larger molecules and you have if you have larger molecules with polar functional groups, you're going to increase the strength of your intermolecular forces, and that will produce higher boiling points and higher melting points compared to smaller molecules and molecules with no polar functional groups. Okay. And so in terms of solubility, and we're going to go ahead and look at two types of solubility: solubility in water and solubility in something that's non-polar. Okay? And so remember the addition of this OH, this hydroxyl group. Since OH is a polar functional group, it'll make this substance more polar. And so since water is a polar substance, if you were to take methanol and you were to dissolve it in water, they'll be able to dissolve. So that's why there's this infinity sign, right? So it's solubility, it's soluble always and always at a specific temperature. So here in this case, it's going to be 20 degrees Celsius. And so the solubilities of these substances changes depending on temperature. Now, when you guys are looking at the solubility of methanol in something that's nonpolar, only 0.12 moles per 100 gram of solvent will be soluble in this nonpolar substance. The reason why is because you have a conflict between this polar functional group and this nonpolar substance. So only a small portion of it, 0.12 moles of the alcohols out of 100 grams of the solvent will actually be soluble in a nonpolar solvent. And so if you guys are looking at ethanol and propanol, notice that these two substances are equally soluble in both water and a nonpolar solvent, such as benzene or cyclohexane. The reason why is because if you guys are looking at methanol and ethanol, so I'm just going to go ahead and use my pointer here. So here we have a 2-carbon substance. Here we have a 3-carbon substance. And so as we increase the carbon chain, we increase the non-polar characteristic of that molecule. And so simply by placing, one polar functional group does not make all of the organic compounds super polar or super soluble. There's this interplay between the length of the carbon chain, which is typically nonpolar, and the amount of hydroxyl groups that's present in that organic compound. And so if there's only one hydroxyl group on each and every single one of these substances, but we're increasing the number of carbons as we go from the top to the bottom, that means that our substance is going to increase in non-polar character, forcing it to not be as soluble in water compared to its smaller, more condensed counterparts. However, since we're increasing the non-polar character of that specific alcohol, it can be dissolved very readily in a solvent that's non-polar. Okay. All right. And so the conclusion is, when you guys are looking at this chart, any alcohols greater than 4 carbons are insoluble in water, or completely insoluble in water. However, it would any alcohols greater than 4 carbons will be infinitely soluble, will always be soluble for nonpolar solvents when you're defining it at a specific temperature. All right. And so where are alcohols present in? So I kind of talked about the idea of these functional groups playing a strong role in terms of medicine, food, beverage, nature, industry, and all that stuff. And so if you guys are looking at, for example, this organic molecule, acetaminophen, that's something that I kind of brought up in a previous lecture video. Acetaminophen is the active ingredient of Tylenol. And if you guys are looking at the structure of acetaminophen, notice there's a hydroxyl functional group. And so tramadol, I believe it's an opioid derivative. So it acts as a pain reliever. And so you'll see that tramadol also has a hydroxyl group amongst other functional groups. So here on the right hand side, this is simply methanol. And so here, this is ethanol. Oops. This is a 2-carbon organic compound, and this is ethanol. So ethanol is typically what we consume in beer and other alcohol-related beverages. If you guys are looking at this molecule at the bottom, we have alcohols present or hydroxyl groups present in this disaccharide, which is a sugar molecule, and we'll talk more about sugars and carbohydrates in the next chapter. And so this demonstrates that this functional group, hydroxyl or alcohols, are just prevalent. It ranges from medicine to stuff that we eat. Also, it's found in biological molecules such as like cholesterol. So here's an alcohol, testosterone, estrogen. Okay. And so all of these functional groups, or this specific functional groups, it's commonly found in a lot of places. Okay. And so here we also have vanillin. So vanillin was a structure that I introduced to you guys when we were talking about benzenes or aromatic compounds. So we also see another alcohol functional group or a hydroxyl functional group that's in this organic compound. And so most organic compounds either have one or a combination of other organic compounds. And so it just really depends on that specific organic compound. So there's no set rule as to the maximum number of no set rule as to the maximum number of functional groups in an organic compound, as long as it follows the octet rule and other stuff that is out of the scope for this course. Okay. All right, and so that's pretty much it for this first lecture video. In the next lecture video, we will start learning how to name alcohols. So we're going to apply the IUPAC nomenclature so that we can properly name alcohols. See you guys in the next lecture video.